Baronesses and barons of button programming, CircuitPython salutations, it's Prof G, and we are going to examine a common problem with buttons that often trips up new makers. We're going to see that when you press down on a button, there are actually a lot of button presses that are generated as long as your finger remains down on the button. Now, there are a few ways to fix this problem. We're going to learn what I think is the most straightforward and useful method in CircuitPython. It's called debouncing, and we'll perform debouncing using the Adafruit debouncer library. Now, we're going to have to modify our button code just a little bit, but very importantly, we're also going to note that there are some changes you need to make when working with the internal buttons of the circuit playground versus the external buttons that you'll often use in projects. We'll cover all of that, so let's learn big. So my CPB is plugged in, I've opened Moo, I've already made a backup copy of the code from the prior lesson, so I'm just going to click on the X next to the code.py tab. Any code I had up here disappears. Then I'm going to press the new button so that I can start coding with a blank screen. And to illustrate this problem, let's first write a program to light up the CPB when buttons are pressed, and that also counts the number of button presses. So button A will light up red, button B will light up blue, and with each button press, we'll also print to the console showing how many times we've pressed the button that's currently being pressed. It sounds like simple code, but we'll recognize problems with our button code, and we'll learn how to solve them using debounce. So first, let's import the libraries we'll need. Import board, NeoPixel, digital IO, which we need for buttons. Then we'll set up button A, just as we learned in the prior lesson. Button underscore capital A equals digital IO dot capital D digital capital I in capital O out. That's the class name that's inside of the digital IO library that's going to allow us to create a digital input output object. And in between parentheses, we pass the location of the item we're setting up for either digital input or output. That's going to be board dot and in all caps button underscore A. Then in the next line, we take that digital in out object that we created and we're going to make sure that it's set up to accept input. So we'll say button underscore A dot switch underscore to underscore input, and in parentheses we're going to pass in digital IO dot capital P pull dot and in all caps down. Now in a future lesson we'll make clear that buttons need resistors. The buttons built into the CPB have an internal pull down resistor that we need to use. Now the resistor just sets up so that we get a consistently accurate signal from our button, but this pull.down bit here is a variable in the digital IO library that lets us work with the type of resistor, the internal pull-down resistor, that we need for the CPB's buttons. But I put a comment in here that says note pull.up in all caps is used for external buttons. So we'll cover this in a future lesson, but it's going to be important to remember when you use external buttons, you're almost always going to say pull dot and in all caps up instead of all caps down. So even though my students are starting their learning journey with the CPB is sort of an anomaly. We usually say pull dot up. We'll see plenty of that in future lessons. Then in the next line, we'll set up button B just like we did with button A. So we're going to say button underscore B equals digital IO dot digital in out. In between parentheses, this is going to be board dot and in all caps button underscore B. And underneath that, we're going to say button underscore B dot switch to input in between parentheses digital IO dot capital P pull dot all caps down. So remember now we've got two objects, button A and button B, and when their dot value properties are set to true, that means they're being pressed. And since we want to light up the Circuit Playground's NeoPixels when we press that button, why don't we create a variable that we'll call pixels, setting that equal to lowercase NeoPixel dot capital N neo capital P pixel, that's one word, and in between parentheses we'll say board dot all caps NeoPixel, that's the location of the NeoPixels on the CPB, comma 10 because there are 10 lights on the CPB. Then let's create our colors. We'll say in all caps black equals between parens 0, 0, 0, blue in all caps equals between parens 0, 0, 255, and red all caps equals between parens 255, 0, 0. Then in our while true loop, remember capital T and colon at the end, we'll press return and we'll say if button underscore A dot value colon, press return, we're indented, and we'll turn on the red lights with pixels dot fill in between parens red, then press return, and I'll outdent by holding down shift and pressing tab, and then I'll say elif button underscore B dot value colon, press return. So this is what we're going to do if button B is pressed. Pixels dot fill in between parentheses blue, that should turn on the blue lights. Press return, outdent with a shift tab, else colon, and if we're not pressing down button A or button B, let's turn all the pixels off with pixels dot fill between parentheses all caps black. Now let's click on the serial console to open that up. We'll click on save. Make sure you click on the CPB and save this as code.py. I'll save over anything that exists there. I don't have any errors in my code. And let's take a look over at our CPB. I'll start off by pressing button B, turns blue, B turns blue again, A turns red, A turns red again, B turns blue, A turns red. Again, as long as I'm holding down the button, the light will stay on, otherwise it'll turn off. Looking good. Now the problem we're going to encounter is when we try to count up the number of times that a button is pressed. So let's add code for that. I'll hide my serial console to give us a little bit more room. Then let's create two variables to hold the count of the number of presses for button A and button B. So we'll say press underscore count underscore A equals 0 and press underscore count underscore B equals 0. Then right after we detect button A is pressed, in this line here, if button A dot value, we'll add a line that says press underscore count underscore A equals press underscore count underscore A plus 1. Then under that, we'll print out our results with an F string with print parens lowercase f double quotes, and in between the quotes we'll say button A pressed curly braces times, and in between the curly braces, we'll pass in press underscore count underscore A. So we'll assume that each time we press button A, press count A will be incremented by 1, and then we'll print out that value. Then we'll do the same down here after the elif button B dot value. So I'm going to highlight and copy the two lines I just wrote, paste them below the elif button B dot value, but I'll change press count A to press count B in 3 places, and I'll also make sure that the string says button B, not button A. And just to make sure that everyone knows, there is a popular shorthand in most computer languages for adding a value to a variable. So instead of saying press count B equals press count B plus 1, we can say press count B plus equals. Those two symbols are right next to each other, no space in between. Then the number you want to add to them, in our case, that's just 1. So these two things are essentially the same thing. Then let's open the serial console. I'll save my work. My code runs without any errors. We're waiting to see some output. So over on the CPB, I'll press button A. And good gravy! I only held down the button once, not 73 times. Press A again. Yikes! It records up to 162 presses. I did not do that. Let's try button B. Whoa! 57 times. Press B again. B's up to 170 times. Back to A. We're up to 245 times. Back to B. 269 times. A. 309 times. Well, this is not what we expected. Why are we recording so many presses when we were only holding down the button once at a time? Well, in order to show what's going on, let's look at how many times we go through the while loop, as well as how many times we're recording that the button is pressed. Now, under the press count variables, I'm going to add a new variable up here, while underscore count, setting this initially equal to 0. Then, in while true, I'll do the same thing that I did down here with press count. I'm going to increment while underscore count by 1 with while underscore count plus equals 1. Then I'll copy this print f string down here, paste it below while count plus equals 1, make sure that I get my indentation right, and I'll change this print f to read while count equals, and then the variable while underscore count will be between the curlies. And now my CPB executes super quickly, and it'll be tough to watch those print statements scroll by so fast. So I'm going to put a time sleep delay in here at the end of the while true. To use time.sleep, I need to make sure that I've imported the time library up here. You can certainly try this without a sleep, but hopefully it'll make it easier for us to see the steps occurring because the text won't race by so fast. So in the last line of code, I'm going to outdent to where the if-else is, and I'll enter time.sleep, and in parens, how about 0.25 seconds, a quarter of a second. Then open the serial console, click save, and look what's happening without me touching any CPB buttons. The while true loop continues to execute, incrementing while underscore count each time we restart the loop. Now let me press button underscore A. And look at this. This line, if button underscore A dot value is equal to true as long as my finger's down on the button. So we're incrementing and printing press underscore count underscore A each time we go through the while loop. Now we're also filling our NeoPixel lights in as red, and if they're already red, we're going to keep that red state. But as we continue through the while true loop, we're incrementing while underscore count as expected, but we're also incrementing and printing button A. That's why we get so much output down here. But we did not press the button that many times. When I take my finger off, we keep going through the while true loop, the lights go off, we're no longer printing press underscore count underscore A. That's because when we're not pressing button A, then button A value is false, so we don't execute what's inside the if. But what we'd like to do in this code is when a button is pressed, we want to only record one button press until the finger is raised. Now to do this, to get a button to register just once for a press, not multiple times when it's held down, we're going to use a technique referred to as debouncing. And there are a few ways to accomplish debouncing. I'm going to demonstrate a method using Adafruit's debouncer library that'll register the press only once, so we'll get an accurate count, but it won't hold up the rest of the code. So we're going to keep going through the while true loop. We're not going to halt the code while we're pressing the button. We're just not going to record more than one button press as long as the finger's down. And here's how we do it. Now, to get this debounced button goodness to happen, we need to do a few things. First, we need to add an additional library. We're going to add Adafruit_debouncer, and since we only need the button class in that library, we'll import it with this line: from Adafruit_debouncer import B button. Now, we're also going to find that this needs an additional library that I forgot to tell you about when we first set up our CPB's lib folder. So we're going to need to add Adafruit_tix.mpy to our lib folder. Sorry I didn't tell you about that, but this is a good teachable moment because we'll get a look at the kind of error that occurs if we try to import a library that's not in our lib folder. So after I show you that error, we're going to go back to our original set of lib files. We'll find the Adafruit_tix.mpy file. We'll make a copy of it into the lib folder on our board. Now, another thing that we change is the way we set up our buttons as well. So instead of just 2 lines, we need 3 lines. And Blink is telling us to watch out the 3 variables, all caps button_A, button_A_input, and button_A are all different. It's really easy to confuse these 3 variables. Make sure you treat them as separate things. Now, we've seen this first one before when we say board dot and in all caps button_A. This is just the location of the built-in buttons on the CPB. So there's a button A and a button B. Now, when we eventually wire buttons up to boards, we're not going to pass in this button A or button B. We're going to pass in the pin number that we wire a button to. Now, the first 2 lines look the same as the lines that we've written previously, but notice that I've changed the name from button_A to button_A_input. And I'm doing that because in this particular case, I want to call my button button_A. So that's the name of the button that I was using previously, but we need to do some changes here because it's debounced buttons. Now, I'm going to set this button up as an object of class type button with a capital B. This is the class that we imported from Adafruit_debouncer above, and what that does is it creates a button that's a debounced button. It's only going to report its state once per press or release, but we need to pass in the initial setup from above, so that's why I call this button_A_input. So when I set up the button_A here and call the button class, I'm going to pass this in as our input here when we create that debounced button. Now, also notice there's a second parameter in the button class, value_when_pressed, and I set this equal to T true. So this value is set to false by default, but there's a weird thing happening with the built-in buttons in the CPB. Now, you see, when we work with buttons, we're going to use something called an internal resistor. Now, not to get too far into the weeds, but we need to use an internal resistor to make sure that our button reports its presses properly. If we didn't use the resistor, then we wouldn't get an accurate button reading. Now, because of the way the built-in buttons are designed on the CPB, we use this P pull dot all caps down resistor here. You'll hear that referred to as a pull down resistor. Most of the time when we work with external buttons that we wire up to a board, we're going to use P pull dot all caps up resistor. So pull dot down for CPB built-in buttons, pull dot up for the type of buttons that we wire up to a board. Hopefully that description prevents us from having to dive too deep into what's going on with electricity on our boards. But there's another thing we need to pay attention to with these built-in buttons. Buttons that use the pull down resistor report true when pressed. The default is that a button will report false when pressed. So that's what this second parameter does here. So the shortcut to remember is when we work with the built-in buttons in the CPB, we want to use pull.down and value_when_pressed equals true. And when we wire external buttons to our board, we're going to do pull.up and value_when_pressed is going to be equal to false, but that's the default, so we can leave out the second parameter for any wired up buttons. Now, one more thing. Each time we check to see if a button was pressed or released, we need to call that button's update method. It's a method. See the parens after it. No parameters are passed into the parens, but this makes sure that we're checking the most current button state. And since this is a debounced button, we only record 1 press each time it's pressed, and 1 release each time we raise a finger off the button. Now remember, we need to call the update method for each button. So if we have 2 buttons in here, we're going to call the update method on each of those buttons. Most of the time, you're going to put this right inside of your while true loop so that you call this before you check the state of the buttons by checking the buttons pressed and released values. So let's go ahead and add these changes to our code. We're going to see how things work. Now we're going to find that our count and our print works great. We're going to run into another snag when it comes to getting the lights to work properly, but I'll show you how we can fix that, and we're going to end up with what I hope is very readable code when we're done. Now, the first thing we need to do is to import the button class from the Adafruit_debouncer library. So we do that with from Adafruit_debouncer import B button. Now, we could have just imported Adafruit underscore debouncer, but that'll import everything in the library, and we don't need anything other than the button class. And this also is going to allow us to refer to just B button instead of Adafruit underscore debouncer dot B button. Next, we'll make the modifications of our button initialization code, and instead of just creating a digital in-out object that's switched to digital input, once we set this up, we're going to pass it into the button class to create a debounced button. And I'm going to want to call that final button button underscore A. So I'm going to switch the button underscore A up here to read button underscore A underscore input, and I'll replace button underscore A down here with button underscore A underscore input. And then below this, I'm going to create our real button underscore A. This variable is an object of the button class, so we'll say equals B button. Remember, that's the class we imported up here from the Adafruit underscore debouncer library. And between parens, I'll pass in button underscore A underscore input. That's the digital input output object that I created up here. Again, this is going to turn this into a B button, which is a debounced button. And I also need to say comma value underscore when underscore pressed equals true. Make sure that's capital T true. And make sure you've got a closing paren. Now, this second parameter is needed because I'm using the built-in buttons on the CPB. You won't need that for external buttons, which use the pull up in all caps resistor. External buttons have a value when pressed of false, which is the default, so we won't need the second parameter. And if you don't understand external buttons now, don't worry. We're going to cover that part when we wire up external buttons in a future lesson. Now, we'll do the same thing down below with button B. We're going to change this to read button underscore B underscore input on both the first line and the second line. Then we'll create a button underscore B the same way, setting that equal to B button, and in parentheses, I'm going to paste in button underscore B underscore input, and it's also going to need this comma value when pressed equals true parameter. Now next, and this is really important, I need to call an update method for each button before I check its state. So in the while true loop, just before the if statements, I'll say button underscore A dot update, open and close parens. So this is a method, it's a function attached to an object. So our button underscore A is an object of class type button. There's a lot of computer jargon in there, but it's important to understand these terms now that you're a CircuitPython programmer. And this update method takes no parameters between its parens, but it will make sure that we get an accurate reading of the current state of the button that it's called on. Now we need to do this for each button, so we're going to do the same for button underscore B, and I'll put a comment in here, very important to call .update parens on all caps each button before checking state. I've seen a lot of students forget to call update on either or both buttons when they're using debounced buttons, and they're wondering why their debouncing code doesn't work. So be sure to include a .update. It's almost always going to be inside your while true loop, and it'll be before you check the button states. And another change, since we're using debounced buttons, that's buttons of class B button, we no longer look at the button value property. Instead, we're going to look at the button .pressed property. If that's true, then the button is pressed. So I'll change value to pressed in both this if and this else if statement. Then I'll open the serial console and click save, and I get the error that I warned you about before. And just as a reminder, since I have an error, I should see my CPB flash twice in red, and it should flash twice in red again every 5 seconds. And down here in the serial console, it says the error is in code.py line 3, but below that, curiously, it says Adafruit underscore debouncer.py line 32 in module. What this means is that there's an error that starts in our code.py file in line 3, but actually takes place inside the Adafruit underscore debouncer.py code in line 32. But hey, we didn't touch that code in Adafruit underscore debouncer. But below we get a clue. Import error, no module named Adafruit underscore ticks. Now, we don't mention that module in our code, but we import Adafruit underscore debouncer, and that module needs Adafruit underscore ticks. So if you ever get a no such module error like this, look to see what you're missing. In our case, it's Adafruit underscore ticks. Then make sure you add that file to your board's lib folder. Now this was an easy error to make because we don't actually import Adafruit underscore ticks anywhere in our code, but that library is used by another library that we imported, Adafruit underscore debouncer. But as long as we can read the import error and see what file we missed, the fix is easy. So I'm going to minimize Moo. I've saved the last copy of the Adafruit libraries file that I downloaded from CircuitPython.org, and I've moved that folder to my desktop so you can see it here. And if I go into that folder, I see more folders, but I want the lib folder. Remember, there are hundreds of libraries in here. You can scroll through these alphabetically, or on the Mac, I can click in this window and then type in Adafruit underscore ticks, and my window jumps to that file automatically. Then I'll open my CircuitPy volume, which is my board, and I'll drag Adafruit underscore ticks into my CircuitPy's lib folder. folder, and I've just made a common mistake. I missed. My library didn't go inside the lib folder. See, it's at the top level just above it, so I'll drag it in there now. I've seen lots of students make that very same error, so make sure your dragging aim is accurate or your board won't be able to find the file that it needs and you'll continue to get the same error. So I'll expand my lib folder and yep, it's in there. Good. And I also keep a backup of my board setup files on my computer. I've copied that to the desktop as well. I called mine CPB setup here. So on my Mac, I'm going to option drag Adafruit_tix into the lib folder in here. Option drag on the Mac makes a copy. Otherwise, I just move the file. Then I'll check the lib folder in here. Adafruit_tix is here too. So I can close these windows, return to Moo, and my code automatically restarted when I copied the files over, so I get no error. But if I click on save again, I start executing code.py from the start. Again, no errors, and I can see my increasing while_count as I'd hoped. But now the moment of truth, I'm going to press my debounced button A, and hey, will you look at that? Even though I'm holding my finger down on A, it's only recording the initial press, but it didn't hold up the rest of my code. The while true continues to increment. So try this out. You should be noticing that the button A count only increases when the button is pressed. Same for button B. Now our lights aren't staying on when the button is pressed. We'll describe why in just a minute, but our press count is definitely working properly. So this is great. But what's up with our lights not staying on? Well, let's take a look. Remember, we said that a debounced button object will only report its state changed once when it's pressed or released. It won't repeatedly report that state change. So, in the if, else, if here, we correctly increment the count, and we also fill in the lights red or blue. But this complex if statement here has an else clause. And this else statement is going to continue to execute on all of the passes of while true after that first press is recorded. So press is recorded only once, but this else clause is going to fire every other time we go through the while loop until another event is recorded. So that's why we almost immediately see the lights go off. It actually happens after 0.25 seconds because we've got the time sleep in here. So we're getting the correct count, but this else statement turns off all the lights because after that first press, neither the if or this else if is true. So with each pass, we say else, pixels black, else, pixels black, else, pixels black over and over again until we record a new event. But the fix is easy because buttons also have a .released property. That'll let us get rid of the else clause down here and replace it with an elif statement, which checks to see if the button's been released. And if a button has been released, turn the lights off. So I'm going to add another elif just below my if clause here. Make sure you outdent the if and elifs all need to line up. And I'm going to say elif button_a.released : then below this, I'll just set my pixels to black. And I can copy this line down here from my else clause, paste it into my elif. Then I'm going to change my closing else clause. I don't want an else clause in here, but this is going to be an elif. And I'm going to set this to button_b.released : I'm going to keep my code down here that turns the lights off. Now let me open my serial monitor and save. Moment of truth. Press and hold A, and hey, the button A press is recorded once, but the red lights stay on until I raise my finger. You can switch between A and B. You'll see that our presses are recorded properly, and the lights remain on as long as a button's pressed. Well, actually, we have a slight delay in here, so I'm going to get rid of the time sleep at the end of our code, and I'll also get rid of this print statement up here with the F string with while count in it. That'll scroll by too fast anyway, and right now I just want to check to make sure that my counts are being recorded properly and my lights are showing up for the duration of a finger on a button. Clicking in a line and pressing Command K on Mac, Control K on Windows automatically adds a comment character out front. Now I'm going to save. Let's try this again. Press button A one time. A second time. We're seeing that the lights are on as long as the finger presses down, but the counts are also accurate. You can tap away at these buttons, Pythonista. Feel good about that slick new CircuitPython skill. You have now conquered button debouncing. Your buttons are responding only once per press and depress event. Nice work! I'll add to my comment up here to say that this is with Adafruit_debouncer, and I'm also going to save this to my CircuitPython school folder, which I keep on my desktop. I'm going to call this CPB with Adafruit debouncer buttons. So feel good about another new skill, Pythonista, and prepare for more big learning. There's lots more to come. Continue to hack.